connector for this thing?
I think it's already connected to the white adapter.
Oh, it's already. Oh, great. Let's see if it works. It is. Okay, awesome.
Okay, yeah. So now we have a talk by Arya Mazumdar. He is a professor at UC San Diego. He works on the intersection of optimization, statistics, and machine learning. And he will talk about continual learning and gradient descent.
Okay. Thanks a lot to the organizers for inviting me to this wonderful workshop. It is always great to be here in Simons Institute. So the talk, the work that I am going to present today, it's a combination of two papers, and there are other people in the paper, but the work mostly has been done done by our postdoc Hossein Taheri, who is, by the way, in the job market. I think it is going to be slightly different flavor than the talks that were there in the morning, but I will try my best to connect, to make some bridges. As you've seen, I am going to talk about continual learning, while this is actually a program on federated and collaborative learning. And this workshop particularly is about learning from heterogeneous sources. So I want to argue that continual learning and federated learning are not too different. In continual learning, as you probably heard of this term before, it's like you have one model and there are like different tasks. That means, and those tasks are coming one after another, and you are training with this data, this model. So this is some sort of sequential training that is going on different type of data sets. Whereas in federated learning, you have a parallel version of it, where all the tasks and different heterogeneous data sets are present to you, like task 1, task 2, and task 3. And then there is a network over here that you are training, like or a model over here that you are training. This not necessarily is a neural network; it could be something else. This is sequential, and while this is in parallel. And I think now we have some understanding that says that at least for linear models, ultimately it doesn't really matter whether you are training with this data set sequentially or in parallel. You will sort of hit the same eventual model, and there will be the similar kind of bottlenecks and walls that you will be facing in both of these cases. So in particular for this talk, we will be talking about continual learning, but I think a lot of those things can be ported over to federated learning as well. Also, I think there is actually an emphasis on optimization in federated learning, which is like the classical optimization theory. Whereas in most of these cases, I think, and this is especially true for continual learning, we are looking at over-parameterized regime. So eventually, there are like multiple models that are good for task 1, task 2, or task 3, in either of these two cases. And we want to go suppose these are like the possible solution or good solutions or good models for different data sets. We want to go to this kind of intersecting points, right? And there is some argument, at least for linear models, that no matter what you do, either you do this or this. If these sets were convex, that would have been really nice. So ended up being these sets we don't have really good control over, like this type of the possible good models. But we really want to, whether you do this or do that, we want to go to this intersection, like one common model that is good for all of the tasks. And due to over-parameterization, that is possible. Okay, so I'm going to in particular talk about gradient descent in neural networks. So I thought I will just give a few slides to introduce the language that I'm going to use over here. So that would be, I think, for quite a few of you, that would be somewhat redundant, but just bear with me when I go through that. So my plan is to give a brief introduction to the theory of the kind of theory that I'm going to use in this talk, that theory of neural networks. And we'll talk about classification problems. So these neural network classifiers in this kernel regime, or the lazy regime, as we are going to call them. And then we are going to extend this to continual learning in neural networks. So that's the plan. I had something about learning XORs, but I don't think there are already enough stuff in here. Okay, so what are neural networks? This kind of a messy picture, but I think it's been 15 years now, so everyone is sort of used to this picture, where you have this multiple layers. There are like a lot of connections over here. Some of these are like sparse connections, whatnot. So we don't really have a good handle. Like you'd hear people saying that we don't know a good theory of neural networks. On the other hand, there are like hundreds of theory papers in neural networks. So it's not a really manageable function. So there is some relationship between y, which is the response of the network, and x, which is whatever is the input. But it's not a very manageable function. So what do we do to make it somewhat manageable? By the way, all these things are well known. Like maybe almost 7-8 years ago, this was known. So we can just write it like this is a summary. We assume that this is some function phi over here, and all the parameters of the model is summarized over here in this w, right? So this is actually, this function depends on w. So we don't know how to handle this cumbersome relationship between input and output. However, we know everything about linear regression, right? Because that's like statisticians have studied that for, I don't know, 100 years now. 2026 already. So what we will try to do is to linearize this function, right? And we can linearize it. So in most of the cases, the way we train neural networks is to start with some initial weight and then run some form of gradient descent or variant of this iterative optimization algorithms, right? So let's take this W0, which is the initial weight vector over here, and try to linearize this very complicated function by writing a Taylor expansion, right? So we do, and we will just truncate the Taylor expansion after the linear term so that it becomes linear. So although this is, well, you can say this is like this is a highly nonlinear relationship, and you are just writing a linear version of this thing. Like you can see this is the gradient of this thing, W minus W0. This is the Taylor expansion truncated at the linear term. So this is not a good approximation. But if your W is close to W0, like if it is close enough, then it's a reasonable approximation. So let's just believe that this is a reasonable approximation by sort of choosing a W by saying that during the training process, my weights are not moving very far from initialization. Okay? So this is going to be a big drawback in this theory that I'm going to present. If you do that, then you can just rearrange this thing. This y minus this response at initialization is now there is some vector over here multiplied by W minus W0. Note that W0 is known. This is the initial point that you are starting from. So you can calculate phi x W0 and this W0 as well. So it's equivalent to saying that my new labels are y prime, which is this, and my weight vector is W prime. So now there is a linear relationship with the caveat that I am very close to the initial point, right? Okay, now you see this is not really x. If it were x, then this would be a linear regression, but it's some sort of feature mapping of x. So we have a feature map, x being feature mapped to this gradient of the network evaluated at the initialization, right? So with this feature maps, this is sort of a kernel regression thing because we know we are very familiar with this, kernel range regression type stuff. So we have, with respect to these features, the output is linear. So we can write a kernel. The kernel is like this, right? So with these features. So now for large number of parameters, assuming this W0 follows some random initialization, and in some special cases like two-layer networks, there is a pretty good approximation for this kernel. Like we can actually write some nice form of this kernel and then use standard results of kernel regression to get some generalization, but because those are very well understood, to get some generalization bound on neural networks. Right? So this has been done, like almost, as I said, 7-8 years ago. And this is called the analysis of the neural network in the kernel regime. And you can immediately say, well, there are some drawbacks in this, and I'm going to come to the drawback. One, of course, I started with the drawback that you are not moving far from initialization. Otherwise, to start with, the Taylor approximation is not very good. Okay. So the width of the neural network, I mentioned it over here. So the large number of parameters, this is actually somehow encoded in the width of the network, right? If the width is large, the number of parameters are large. And you see this network, if you think of just, say, idealize a shallow case where you just have a two-layer network, the function looks something like this, right? It's, J's are sort of the outer layer weight, and this then there is this activation function, and WJs are the inner layer weight. Okay, so if it is some sort of sum over this M, and we can properly normalize it, and as M tends to infinity, we can have a nice form of the kernel with respect to, we can write it, it sort of converges to some expectation with respect to the initialization, right? So if you have a very large width, then this approximation is valid. So that's why people talk about neural networks with, there is a lot of results that are valid for very large width. And then the aim is to make it finite width. Okay? And the large width somehow felicitates this kernel regime. If you have a large width, that is an alternative of taking small steps. Well, again, why are we taking small steps? Because of this drawback that we are not moving far from the initialization. If you recall the feature map, right, it is going from x to this gradient of phi evaluated at W0, right? So the feature map is actually fixed at initialization. So a major drawback is that during the training, we are not really changing this feature map. So the neural network is not really learning new features. That's why people say, OK, this is not good to explain feature learning in neural network, and we should do something, some different kind of analysis for feature learning. Okay, so one question over here is like that the people were trying to do, like up to what radius this kernel approach is valid, like how far can you move from initialization? Because if you move farther from initialization, then of course this approximation falls apart and this analysis is not valid. Then the question is what happens with large step size, right? Because if you're taking large step size, you go outside of this regime. And how new features are learned in neural networks by taking these large steps. So these are like outstanding questions, and many people now spend their time on evaluating these things. Okay, good. So these are the terminologies that I'm going to use in the remainder of this talk. Okay, so I was talking about a regression. If you go back this y and x. But this is true for neural network classifiers as well, where at the end, I'm just putting a sign function. So let's restrict ourselves to binary classifiers. So then I will just put, I have this phi xw just as before. Then I'll put a sign function to make it a classifier. And then this will, the same theory that we have developed for regression in the last couple of slides, that's going to be valid with, instead of a kernel regression, we'll do something like a kernel SVM, which is again well understood. And we need some sort of separability condition, because that's what people do in in traditional kernel things. So the separability condition is a margin condition like this. Recall, this is the feature map. So we are saying that there exists some W such that with respect to this feature map, the data is separable by some margin gamma. So this has been a standard assumption in a bunch of papers that came out around 2019, 2021. So like in I think in ML terminology in a previous era. Okay, so now based on this, there are actually some results. And I think our first contribution that Hussein, once he came in as a postdoc, was to improve, get some improved result over here. So we can define the loss function. Since it's a classification problem, we can define a correlation loss like this, where the loss function is actually a function of the correlation between y and the prediction of the network, which is again a usual thing in classification. For example, the very popular logistic loss. We can define something, we can define the empirical loss function. So if you have a bunch of samples, and this is just the sum of all this loss evaluated over those samples. You can also have a population risk function. Now, This has been analyzed, the neural networks have been analyzed in a bunch of papers, and I think these are the closest that we have found, the results that are comparable to ours. And if we have a ReLU activation function, this gamma is the margin of separability, right? And the width, recall it's M. So all this analysis has been done in the kernel regime, so that you need some sort of width requirement. Then it can be shown that after running gradient descent for capital T steps, your training loss is going to go down as 1 over gamma squared T. Okay? And the test loss, so there are some generalization results as well, which is this 1 over gamma squared T plus something. So this was what was known. And you see this is not fully satisfactory because it is like there is some exponential O. This is L is the number of layers in the network. Okay, so this is actually growing with that. And then there is in the generalization results, there is the square root of M over N. Again, M is the width, N is the number of samples. So, well, it's some results. We can actually come up with some sort of new stability-based analysis that would give us with the same width requirement, and we'll have the same training loss, but an improved test loss and improved generalization results, where we can get rid of the square root of Mn and instead, so there is no dependence on M, and the dependence on N is actually improved over here. Okay. Sorry?
What is M?
M is the width of the network. So we assume that it's a L-layer network, and each of the number of neurons in each layer is M.
And what is the width?
So this is the width.
So
okay. So it has to be at least this. Otherwise, this is not going to be valid.
Okay,
Like
so
this result, there is a requirement of that.
Okay. So,
yes.
So now M is at least that for what? Okay. Let me tell you my confusion.
Yes.
Let me
Yes.
tell you my confusion first. Gamma is defined with respect to.
This is somewhat roundabout. Yes. Yes. Gamma is defined.
with respect to
This is the gamma.
This kernel,
Right.
right? But the
Yes.
kernel is assumed what, in the infinite width case or in the M greater than?
It's the M greater than that case.
Okay. So if M is greater than
That, then you will get.
kernel with respect
We
to
assume that
just a
the
function that has M, and that you assume that if on top of it it has the data has separability gamma, then you have this.
Right, exactly. Yes, very good. Yes, and again, we can show that the radius of the kernel regime's validity is now can be growing with this width. Okay? As long as the width is bigger than this, we can it actually grows, but it's like grows like this. So this is good because previously we in this result, for example, this has to be a constant. So you cannot go more than a constant away. Now this can grow with the width, albeit not in a very favorable way, but it's a growth. Yes. Yeah.
Yeah, so we talk about test error loss, that's good. So, but you gotta have some assumption on the population. What is the assumption?
I will tell you. So the detail of we want some sort of smoothness property. The activation functions have to be smooth. We cannot work with the ReLU activation, and the network also have to be Lipschitz. So that's that type of thing.
I was talking about the population distribution of the data.
As long as the margin condition is satisfied, it is fine. So you can come from.
But the margin condition was defined on the empirical set, not on the population.
Yeah, I don't need anything else on the population as long as it's a correlation like this type of logistic loss. So there is no depend. It could be something else, and the margin condition is satisfied on the overall.
Those make sense, to be honest.
You mean to say that? Okay. So this also has okay. So I think what you are saying that if you have an x and y. Like in the population sense, also this margin has to be true, like something like that.
Do you have that or something?
I think we do. We need that. Yes.
Okay.
Yeah.
So, okay. Good.
Yeah.
Then this 1 over gamma square n.
Yes.
Is like a well-known bound for linear in the kernel case.
Right.
I was just wondering why the previous result has this square root m dependence there, square root m over n.
For the generalization bound.
Correct.
I think they have this because they go through a Rademacher complexity-based thing. That's why.
Like when m go to infinity, this whole system go to a fixed.
So this is, yeah.
The test error shouldn't grow with width. That's something.
Yeah.
Anyway.
Yeah,
Yes.
it's a simple question. Are these rates for all ranges of gamma or similar ranges of gamma, or some results are for some ranges of gamma?
Gamma, just think of gamma as something fixed. Yes.
And, okay.
And all it is separate. There is no other requirement. Okay. Yeah, I see what you were saying, but yeah, I can go into that. Okay, so how is this being proved is something like this. So as like for the training loss, and I will come to the test loss after that. We are sort of relying on the fact that we assume a smooth activation function. That means the double derivative of the activation function is upper, like the absolute value of the double derivative upper bounded by some constant. And we are also we can show that the network is Lipschitz. Then we have some sort of self-bounded weak convexity property. So this is the weak convexity property. If you have this kind of things, then the minimum eigenvalue of the Hessian of the loss function, that is, so if this were greater than equals to 0, like that this would be convex, right? So it's not convex, but this is lower bounded by some quantity, which is this. Yes.
One question. So if the activation function, so you're assuming that each activation function is Lipschitz
And smooth.
and smooth.
Yes.
So it's definitely Lipschitz. So
Yes.
then the whole network is Lipschitz, but
Yes.
the Lipschitz parameter that depends on m.
With a Lipschitz parameter, that is actually yes. So
So
it depends on yes the Lipschitz. Well, I can
if
have.
I were to inherit the Lipschitzness of the network from the Lipschitzness of the
It
network,
yes, it is just that.
depends on m.
Yes.
So this additional assumption, in some sense, can be viewed as hiding m into that second Lipschitz parameter.
That is true, but the dependence that I am actually showing you in that table, that takes care of that.
Okay.
You are
I
right.
can
Yes.
ask you some
Yes.
more
Yes.
of-
Yes. Okay. So if you have this, then actually you have something like a descent lemma. It's like one-step progress like this. So you can just write out the Taylor series of this, and then use this self-bounded property and the weak convexity property to derive something like this. This is sort of one-step progress. And after this, you use some telescopic sum and some usual, like some local quasi-convexity properties of this network to get to the test loss. So that's like a pure optimization thing.
I guess the reason I'm asking is because one of your results is saying how far you can go away from W0, right?
Right.
But how far you can go away from W0, I can make it arbitrarily large if I make. I mean, because you have to.
Because if you have arbitrary like large yes.
No, not just your bound. I'm saying to understand the meaning of your bound, I need to understand the smoothness properties of the original function.
Right. Yes. I mean,
Because I'm saying, just saying that I can go 5 away or 10 away is not meaningful if I rescale the whole function and the whole problem.
that's true. Yes.
So-
Yes.
so
So
it's
there
not
has to be. There has to be. Yes. Yes. So for this, let's just we assume that let's say the smoothness of activation is 1. Like it's like a quadratic, something like that, like half x squared. So that's the activation function. Then the Lipschitz constant is 1, and the smoothness is also 1. Then the smoothness of the network is going to be a function of like how I have designed the network. Yes,
But
in that context.
reconcile everything, given that you also assume there is this parameter m that is really an important parameter, the m, but you also assume.
So there are two things. So first of all, you can just treat this result as standalone and forget it. This is sort of it. So this is some sort of intermediate observation that this analysis that we are doing is still valid as long as this happens, right?
Yes,
Okay.
some of my questions are a bit tricky, so let me ask you offline.
Sure, but that's good. Okay. Well, what we want to do eventually is to then do continual learning with this. So it will become, yeah. So the test loss thing, So we use this sort of like some results specialized for neural networks on algorithmic stability. So if we assume that each sample loss is some G Lipschitz for all data points, then this test loss, there is some generalization bound based on stability of the leave one out parameter estimation. So WT, and this is this result that we use it as a lemma. So what is WT? This is after you run gradient descent for T iteration. What is WT minus I? Is you do the same thing but leaving out the ith sample, right? So it's like leave one out sample and WTs are going to change. So if it is the stability analysis, like this lemma basically says that your generalization bound, sort of like if this WT and WT leave one out is not too different, then you have good generalization bound. So then you have a bound like this. So what we do for this is to sort of look at the gap over here, try to bound this leave one, like what is the new WT, what exactly is the bound, right? So, and since again we have some sort of quasi or weak convexity type results, we are able to do that. Okay.
We're missing a square, I think, right?
You mean over here?
Yeah.
Were there a square? I don't think we. Yeah, I don't think there were a square. Yeah, but there might be variant. Like there are other stability results that are slightly different. Maybe in effect they will give you the same thing. Okay. So that's how we get the test loss. Yes?
Just to clarify, you can get the same bound using grammar complexity as well.
Can you?
Yeah, you can do that. The author of the first paper you gave there, they have a follow-up paper using grammar complexity to derive the same wall gamma square and bound.
Okay, maybe that's true. Yes, yeah, sure. Yeah, there might be that. Okay. Good. So this is how the analysis works. So one major drawback of this is I give this, give this sample complexity type results, but there are actually no lower bound. I don't know whether we did is optimal or not. Whether like is it any good, or like should someone else work on it and can get a tighter bound. On all the parameters of m, gamma, and like is there like a better trade-off? In some cases we know, but there is no, the standard way to get computational lower bound is like this SQ lower bounds and stuff, and they're not speaking to all of the parameters that we have over here. So this is a bit ad hoc that we have some results, and the only way for us to verify whether these are any good is to sort of do some simulation and see how the training loss actually behaves, and then whether our results are tracking that or not. Like we don't have good lower bounds over here. And I'm not going to go over this in the interest of time, and also then I have to read these things which are not readable even from here. So the bottom line is this sort of track the experimental results, the kind of scaling that we obtain. Okay. Now the question of continual learning is that can we keep learning as new data comes in, right? So if you do that, train this classifier with some data set. Now suppose your task changes, and you are training it again with this new data, starting from an initialization, which is the final point of the last gradient descent iterate, right? So that's where you are starting from, and it's been it's pretty well studied as well. Empirically, there are like a lot of papers, especially starting from 2013, when there is this observation that if you update a model with new data, then there is some catastrophic drop of performance, and people call it catastrophic forgetting, right? So you train a neural network, new data comes in, you train it with them, and then there is a sudden fall, and it's not recoverable. So this plot is from this paper by Kirkpatrick et al. It's a very influential paper in continual learning and forgetting, and they have this, this visualization over here. So this is basically showing something that I had in the very first slide. So they are saying that, so theta A is actually a low error point for task A. So this set is the low error set for task A. And since these are over-parameterized network, there are many such solutions. And then there is for task B, which is over here, there is a set of good solutions. And what you actually want to do is to go to the intersection of these two. So if you just train, instead you follow this blue path and go to some point over here. So there is catastrophic forgetting for the first one, right? And so they propose, so if they propose some regularization, so this is like elastic weight method, so that actually takes you to this, but this is empirical, like there is no theoretical result that support that you actually go to those points. And we did some simulation, and it is actually observable with some simple data set. So this is some simple classification data, and this is the training error. So you see we have three different tasks, and this is the training error going to close to 0 for the first task. We start training with a second error, it goes up slightly, but then we start training with a third task, and then this is actually increasing significantly. So the forgetting starts, right? So our idea, can we characterize this forgetting in terms of the parameters of the networks and the number of samples, so that we have some sort of sample complexity bound? So that's what we want to do. And again, as I said, there are actually quite a bit of work in the past. One thing that you can observe, that regularization will keep forgetting in check. Right? If you somehow constrain the newly trained model to be closer to what if the first task's good model, and that is a trick people use in federated learning as well, right? So they try to so that there is this for different tasks the models, so that they don't drift too much. So they try to regularize it to some central model with respect to some central model. So regularization will keep forgetting in check. So if you don't, again, this is some sort of this screams the kernel regime, because you are not moving far from where you have started from, right? Also, the observation, there is some observation that we need an over-parameterized setting or the interpolation regime, because otherwise, if you train the model with some data set, and if now you are training with some new data set, it's of course going to forget. Like if you think if it is not over-parameterized and you just have linear regression, now it will learn a new line, and nothing about the old line is going to be preserved. Okay. So for linear model, these settings were actually pretty well analyzed by Nathi's group, and then there are other folks as well. So assuming that there is a single linear model that can interpolate all tasks, you can actually show that by doing gradient descent, you go to such a model. If such a model, so there is, it means for the case of classifiers, there is one single classifier that is good for all of the classification tasks that you have. Okay, and this work actually uses the results of implicit bias, because you are running gradient descent, and for classification tasks with logistic laws, that they will go to, say, the implicit bias is to go to the max margin solution, right? So you use this implicit bias property continually, sequentially from one task to another task, and you can show that you eventually go to a good point, right? So that's the problem of using this type of results for neural networks is that the implicit bias for gradient descent in neural networks, although tried, it is not very succinctly expressed, or it is not expressed in a form that makes it useful in analyzing this type of continual learning setups. If it were there, then we could actually use it. And also, as I just said, if you, yes?
What is the implicit bias here? Just the fact that that a single linear model can interpolate?
No. The implicit bias is actually like, since you are running gradient descent, suppose you have the first task, which is just a classification task, and suppose you are using logistic regression. You can show that there are many possible solutions, but it is not going to go to any of them arbitrarily, it is going to go to the max margin solution. So that's the implicit bias of the, so now there is some characterization of what happens if you run gradient descent for a large number of steps, right? So you can use that start from that point, you can actually show something, right? Okay. So since we are not moving far from initialization, which is equivalent to regularizing it, you stay in the kernel regime, and based on that observation, there are some analysis of continual learning in kernel regime. There is, as I mentioned previously, although like somewhat hand-wavily, that if your width is large, you sort of stay in the kernel regime. So people also showed like that what is how much your kernel, the dependence of learnability, how much you are retaining as your width go. There is some empirical works that study that. One thing that is missing is learning features in continual learning domain, and what would be a natural sequence of classification tasks for feature learning. Because when you are doing feature learning, you start with some data generative model that has some ground truth directions, and then you sort of see whether the neural network is learning those directions, right? So we tried to do that, but we failed. We cannot really even came up with a setup for feature learning in the continual learning domain. So I think that's the major open problem. We ended up still being in the kernel regime. However, we were able to, we ended up getting some data generating distribution. I know that fortunately Ben Recht is not around, but when I was making these slides like a couple of months ago, the day I was making it, there was a blog post that says there is no data generating distribution. And I'm like, okay, that is a bit troublesome, but well, what we are going to do is to assume some data generating distribution to do the analysis. Well, and that's why I previously had the background of XORs, but now I remove it. Let's stick to this data generating distribution. There is a classification task where I am assuming there is some distribution that the samples follow, okay? And my task is like as I go from task 1 to task 2 to task 3, the parameters of this data generating distribution changes. So we do this type of XOR clustered data, which is not very uncommon. Other people have also used that as a model of classification.
Just to understand, what is the goal in continual learning? So,
right.
Is it to not forget? Is it to forget? Is it?
No, it is to not forget. It is to retain.
No, but I don't understand.
It is to retain, because suppose you have you have a model and you have trained it to translate from say German to English, and then you do, like that's
I'm just thinking about a simple situation. The data is changing. Then now the data is in some new state. It's a completely new, different distribution.
Mm-hmm.
And then I want to forget. And
yeah, that's the mission. That's the unlearning stuff. And here I actually want to have a model that if I fine tune with new data, I don't want the previous capabilities to go. So that is the question. Yes.
The underlying assumption would then be that there exists a single model that's well.
That's the right. That has to happen. That's the point I'm trying to. Yes.
Okay, so
yes.
let's assume there is such a single model. Can we not forget?
Can you not forget? Okay. Yes. Well, there is another way you will not forget is if you don't go very far from the model of the previous, right? So that's
really bad, right?
You cannot forget and do really bad. Yes. So there should be some balance. Yes.
So there is a chance to do really well.
Right. So that's why there is like in the new task you want some generalization results and also some delayed generalization results because of this forgetting thing. Right. Okay. Good. So the data generation model is following. I'm just writing it in 2 dimensions, but like we can just. So it's like the XOR, right? So if your data is if your X is in first or the third quadrant, then you will label it with +1, like Y is +1, and if it is in the second or the fourth quadrant, you will label it with -1, like the standard X thing. So instead of having a fixed vector over here, I'm just adding Gaussian noise, because that's actually going to make our analysis easier. So this is how x is going to be a mixture of Gaussian. If y is +1, it is a mixture of another symmetric Gaussian if it is -1. Sorry, symmetric mixture of Gaussians, because you see this mu plus and minus mu plus and mu minus and minus mu minus, right? And the reason to go to this XOR type data sets is that you need no linear separate, this is not linearly separable. So you need a neural networks to separate this or something else. So that's why this is it's a good model of data. For continual learning, for kth task, how am I doing with in regards to time? Do I have 10 minutes? Okay, good. Yeah, so continual learning for kth task, you will have a different mean vector for the Gaussian. So that's why, so you can have a natural sequence of tasks. And now what I'm going to do is to sort of, for each task, I will start with some random initial model parameters. Then I will load the first data set. For up to capital T steps, I will either do a stochastic gradient descent or a gradient descent and update my model parameters. For the second task, wherever I stop, I'm going to set that as the initial point for the second task. And then again do the gradient descent up to, say, capital T steps. And I go on learning this for as many tasks as I have. Okay? Okay? Yes?
Would you be allowed to store previous models and do something with them?
No, I'm not allowing that. My model gets updated through this process as I train it, or I fine tune it, or do whatever language I use. Yes.
I guess there could be some benefit to storing previous models.
I mean, if you could store the previous model for that, then you have a task-specific model stored. I mean, there is no continual learning. You can just store, and then there is a new data set. You are just training that, right? So it's as if, yeah, like in the case of federated learning, it will be like each of the clients have their own models. Yes.
What's FHAT? Say with regularization or without regularization?
There is no regularization. I'm not assuming regularization here. It's not EWC. So I think we were able to show, at least for our analysis, the regularization actually doesn't make a difference if we do L2 regularization. Like if you want to be close to the previous model or some base model by doing L2 regularization in the loss function, that's not going to help in the analysis that we are doing. Okay, some other type of regularization might help, don't know. And in some other analysis, it might help. In reality, it might help. Okay, so it's the same setup as before, except we are not doing a L-layer network anymore. We are stopping at 2-layer because it is actually getting pretty complicated. So this is how our network looks like. This is 1 over m. Then there is a quadratic activation, wi transpose x, this thing square. Ai is the outer layer width. Okay, and we choose these AIs and fixed, and we are only training W's. Okay, so that's our gradient descent is only on W's. Okay. So we define something called test time forgetting. So what is test time forgetting? This is okay. Recall, like this Fk. This is the population loss for the kth task, right? So capital K is bigger than little k. So this is the index of tasks. So capital K is something down the line, right? So at the end of learning all capital K tasks, you have this Wk, right? So this is your model parameter. So you're plugging in W capital K into F little k. So it's a previous task's population risk function, right? And then this is what would have happened if you have plugged in the population is W little k, right? So this is the parameter you learned while you were learning this kth task, right? So this is the test time forgetting, right? So because you went from capital K onward to learn bunch of other steps to achieve at from small little k to you go to capital K, so you have forgotten something about the previous little k task, right? So this is the test time forgetting. We are doing it with respect to the population risk function. So we are going to decompose this into two parts. How we are going to do this? First, we expand it in a standard way that is like you might have seen it. Like we add and subtract the the empirical risk functions to these things to get some individual generalization. So this quantity. So first we have added, subtracted the empirical risk function evaluated at capital W capital K for the little kth training time. Then to nullify this, we added this and subtract from it whatever happens with W little k, and then we basically take care of this last term over here. We can see that at the end we have over here we have something like fk hat wk. Now one thing we do that we assume instead, like we are not assuming logistic loss anymore. We are assuming hinge loss. There is a reason. Yes. No.
Sorry. Why do you want to look at test time forgetting and not train time forgetting?
We can actually show that this test time forgetting can be decomposed over here into train time forgetting and a delayed generalization gap. That's where I was getting to. So yes, we do look at train time forgetting. So this is the point. So the reason we took this to be hinge loss is because if it is in the interpolation regime, then this can go to 0, right? So this is going to be a net negative over here. Therefore, this test time forgetting can be decomposed into this first two terms. Now, one of these two terms is the same thing, but with the empirical risk function. So this is the training time forgetting. And the other term is what happens. It's like a generalization result, but now this is a generalization results for a parameter vector that has been obtained down the line, right? So it's not W little k anymore. So this is some sort of delayed generalization result. Does that make sense?
Just to make sure your optimization problem is quadratic, right? Because you fixed A and then only.
Well, I still have the hinge.
You said you have quadratic activation, right?
I do have quadratic activation.
It's quadratic optimization.
Not really. Like this depends on the loss function, right? So I'm optimizing for the loss. So
Loss is still
hinge loss.
Okay.
Yes, I mean it's still nicely well behaved and everything. It's very nice. It's locally it's convex. Okay, so now our result is actually two separate bound. One is on training time forgetting, which is some sort of optimization bound, and then one is delayed generalization gap. This is actually we use the stability based analysis that we did before. This can actually that can extend to this case. So for the train time forgetting, again we have Lifshitz and like overall network becomes Lifshitz, and the loss function is the hinge. We have the hinge loss, but these are all smooth because the activation function was quadratic. So we have these nice properties. So with that, and we have almost similar type of properties that we have obtained for the previous optimization problem that we have showed. And we can get some results like this. And I will go over this so that we can interpret what is going on over here. So n is the number of samples. Like I'm assuming each task has same number of samples. D was the dimension of data, and then M was the width of the network. Now this result, like we have to carefully choose capital T to be order of D square, and at the same time I think we have to choose N to be something, N to be D squared times capital K, so that actually all of these terms go to 0. Because if you don't choose, like otherwise one of them is going to go to 0, the other one is going to go to. So there is just a choice of T and N that you can make so that all of these terms going to go to 0. The slowest would be this middle term, where we will have 1 over polylog d decay. Okay?
So big T is what, the number of iterations per?
Total. Did I say, yeah, let me just check in the, I think it is the, no, it's not the total. Yeah, it's the per task. Down, this is actually,
task, right? Yeah.
yeah.
Okay. So, okay.
Right.
And eta is a single gradient step.
Yes.
But the same gradient step in everything throughout?
Yes.
Okay.
Yes. So this we are not changing. So by playing, again, there are no lower bounds. So by playing with these things, you might get something. And at some point we said like, okay, this is where we are going to stop. So this is, yes.
But is this assuming the kernel regime, or
This is in the kernel regime.
how do you say that it is the kernel regime?
How do I say this is the kernel regime? Is
You're not parameterizing the initialization in a weird way. You're not scaling the learning rate. So how?
I think it is like it is sort of the feeling that the same type of analysis that we are doing for the kernel regime as before. So it probably okay, and we are also not learning any feature. There is no so.
But who says that you're not?
Maybe like even in kernel regime you may learn features, right? So that's the.
No, I mean.
Who said like okay we have some like but I don't know like these directions are not recovered like we don't have any results like that.
But I mean,
Yeah.
here your analysis applies to the kernel regime, but then the definition of the algorithm is not in the kernel regime. So
I guess the question is the analysis seems more general than the kernel regime.
I think it is, yeah, our objective was not to be in the kernel regime, of course, but we don't have, I think we are still in the kernel regime because of the requirements of width and like our width is very large.
but somehow it seems like you're assuming somewhere that you are in the kernel regime, but I don't really see where. Because else, if you assume it, you are. If you are, if you don't assume it,
Yeah, you are right. Like, okay, so by assuming in kernel regime, what kind of assumptions do you think?
like scaling of the network, 1 over the square root of the width. You initialize with that scaling, and so you converge to the kernel.
I think well, okay. Our initialization has some conditions like that. Yeah, so maybe that's that.
Did you also have any further constraints on eta, or this is the only one? Eta.
This is the only one.
So you don't need anything else on eta. They are not like assuming anything to be in the kernel regime on eta.
No, there is nothing to. Yeah.
You either choose.
Either you choose the M and the initialization in a way that it becomes that, or yeah. So
M
it's
is kind of chosen. You're saying here that.
M has to be carefully chosen to be this. Yes. Yeah.
Which is scaling with what is D and what is K?
D is K is the number of tasks, like the subsequent task, and D is the data dimension. So the way M is related to little n and t is through these parameters D and K. Okay, so yes.
So this XOR problem is separable in the kernel space.
Yes.
And then, like, are you kind of calculating the gamma in this problem and then using your prior results?
Not really. We are not really doing. No. We are just directly using the fact that X is Gaussian, like it's a mixture of Gaussian, like that. What we
But I
have.
think it should be separable in the kernel.
It is separable in the kernel space, I think. So technically we could. I think we did that and it was getting slightly worse result than this.
Worse than
Yes. Yeah.
I mean, how could it be separable? There is no.
With high probability.
Gaussians, yeah, but with the Gaussian.
No, with the feature mapping.
No, even with the feature mapping, because your base decision boundary, right?
Mm,
Your base decision boundary allows overlap, so the base error is non-zero. So there is no way it can be separable in
You
kernel
can say
space.
with some probability, with high probability separable.
With high probability, the data could be separable.
The data.
But then you don't have separability
Oh,
with
the
respect to
population.
the population, yeah. Because the base error is non-zero.
I see.
Will the base error be non-zero even for the hinge loss?
For the hinge loss, I don't know, but I'm just
Yeah.
assuming the
No, so I think that is also like we couldn't make it work with logistic loss. Yeah.
Because the hinge loss is even harder, right? The hinge loss is penalizing even more, not just classification error, but it's also penalizing margin.
Yeah, but that's like, yeah.
I don't think it matters so much.
Yes,
but,
yes. Okay. So for the delayed...
Does it feel from the rates that you're relying on any separability, or that, I guess...
We are not explicitly using the separability thing, but we can sort of get some sort of gamma, assuming this, and yeah, I think we can get some sort of gamma. It will be a complicated calculation, but if with some high probability, we will get a value of gamma. Plugging it into our previous result would not give you this. Like, it will give you something which is worse than that.
I don't see how your hinge loss is dominating the 0-1 loss, so the 0-1 loss is positive, so I don't see how your separability with respect to...
Why do you say the 0-1? The data is the 0-1 loss is not positive, right?
The 0-1 loss will be positive even for the base, right? So there is no function that achieves 0.
But it will be arbitrarily close to 0, right? I mean, depends on the Gaussian. Like, if it were just not...
on the Gaussian, but
yes.
You have to be looking at the, how do you call it, the margin between the means. You have to view it as an asymptotic.
Yeah. So just assume that this mu plus and mu minus are large enough. And they, we are also assuming them to be orthogonal, right? So...
I think we can...
Yeah. Okay. But I think that is actually not the main message over here, yes. But I'm very happy that we have this. Okay, good. So we have a delayed generalization gap, which is similar stability analysis that we have seen. This is not very nice looking, but we have something for the delayed generalization gap as well. Just following exactly the same stability analysis of this leave one out error that we did in the previous case. So we could extend that to this delayed generalization, and as a result, we can show that both this training time forgetting and the delayed generalization gap can be made arbitrarily small. So therefore, continual learning is possible up to k different tasks. Okay. Assuming yes. Okay. So again, so this is actually like the simulation of this thing, and we can actually, well, there are some curious thing that let me just not go to this thing. Like, we can see the impact of width and everything in this plot. So let me go to the outlook of this, because I'm already, I think, 15 minutes over time. Okay. So one good thing, this was not very satisfactory because we started off by thinking if there is some feature learning in continual learning, and we were unable, and that's why we came up with the data distribution model, but then we just didn't know what that would be like. Even we couldn't even well form that question. So that would be, I think, a big thing, at least from a theory perspective. If we can have a setup with, say, a single index model or a multi-index model, and say, okay, we can analyze feature learning and neural network with continual learning in this model. One other thing is we don't have anything about how task correlation affects learning. However, our models, the data model that we have taken, you can easily incorporate correlation by doing some correlation between the mu vectors that we have chosen. Like, we can actually have the inner product between those mu's to be something as opposed to 0. To make not all these tasks orthogonal, but somewhat correlated, right? And then we can see how this task correlation helps in continual learning. And I think that can be a more immediate enhancement to our analysis. Right, I think, so there are a lot of questions, and we hope that this can be a good starting point to look at this thing. So that's all. Thanks a lot for bearing with me, and these are the two papers that, so this one is already published last year in ICLR, and this is actually right now submitted somewhere. Okay, good. Thank you.
Thank you very much for your talk. And we have a break now. And yeah, if you have some questions, you can catch Arya during the break. Yeah, we will start at 3.